myself Dr. W. P. Vinode from Coulsons M, Nagpur. Today I am going to talk on the molecular orbital diagrams of heteronuclear diatomic molecules. In the previous part, we have discussed about the molecular orbital theory and features of molecular orbital theory and the molecular orbital diagrams of homonuclear diatomic molecules of secondary elements. And now today we are discussing the MO diagrams of HF molecule, CO molecule and then NO molecule. So the topic is MO diagram of heteronuclear diatomic molecule, and already we have seen the molecular diagram for homonuclear diatomic molecules. And now in the next slide, so in this case we are discussing three heteronuclear molecules. One is a hydrogen fluoride, means HF, and second is a Coulsons M diagram for CO, and third is a for NO, nitric oxide. So first is a MO diagram of HF molecule. So in this is one is a hydrogen, second is a fluorine, and this HF molecule two atoms are there, and these are the two heteroatoms. And now here hydrogen have the configuration 1s1 because atomic number is 1, and fluorine has atomic number 9, and therefore electronic configuration is 1s2, 2s2 and 2p5. So now here there is a we have to see here that because of the 1s orbital present only in a hydrogen, and 2p orbitals are there in a fluorine atoms. So 2p5 means 1s2, 2s2, 2p1. So one unpaired electron is there in one of the p orbital of the fluorine, and therefore this shows that there is a formation of one covalent bond, and in this case the only the px orbital is able to combine with the 1s orbital of the hydrogen. The combination of py orbital or pz orbital with s orbital is ruled out on the symmetry consideration, and these orbitals are called non-bonding orbitals because they are already having the paired electron. So 2px orbital of fluorine give the highly effective overlap with the 1s orbital of hydrogen and to form sigma HF bond. And now here MO diagram for this therefore is shown in the here molecular orbital diagram is shown here. And again now as we know that there are three parts. This is one part for hydrogen, this is second part for fluorine, and in the middle there is a molecular orbital diagram. As we know that AO and AO combine to form molecular orbitals. So this is the concept to form the molecular orbital. And now after that, so energy level diagram is shown here for HF molecule. And now in case of fluorine, 2s orbital having this is the non-bonding, and the energy is same and shown in the middle. This is lone pair. And another now here is in case of 2p having 5 electron, 1s having, so only one effective overlap is there, 1s and 2p x orbital, x, y, z. Y have 2 electron, z have 2 electron, x have 1, so 2p x and 1s orbital overlap and forming the bonding sigma sp and sigma star sp antibonding orbital. So when 1s and 2px orbital overlap, forming bonding and antibonding sigma sp and sigma star sp orbitals. So here and remaining these are the paired electrons are of the 2p are remain as in the same energy level. They do not take part in the bond formation. These are the lone pairs 2py and 2pz. So there are three lone pairs. This is one and these are the two. Only the possibility of formation of bond. Only one bond formation is there between hydrogen and fluorine, and that is between the orbital of 1s of hydrogen and 2px of fluorine, and forming this bonding electron pair is here and antibonding orbital is here. So this is the MO diagram for HF molecule. And now here this py and pz cannot be overlap with the because of the symmetric consideration with the s orbital. Only the 2ps can give effective overlap with the 1s orbital of hydrogen. And here after this diagram, now see here the molecular orbital configuration of HF molecule. Again now we know that first write the molecule HF, then colon, then K, because in case of fluorine 1s orbital is completely filled, and in case of hydrogen only 1s having 1 electron, so it is taking part in the bond formation, so only 1 K you have to write. And after that start from this 2s2 sigma sp2 and then 2py2 2pz2, but only the molecular orbital is only one which contain electrons, and antibonding have no electrons. bond order can be calculated on the basis of this hemodiagram, and calculation of bond order formula is Nb minus Na upon 2. So Nb means number of electron in bonding. So in case of bonding, only 2 electrons are there. So 2 is there. Here is 2 bonding electrons, and 0 for antibonding. Antibonding have no any electrons. So 0. 2 minus 0, 2 upon 2 equals to 1. So bond order is 1, indicate that there is a single bond between the two atoms of hydrogen and fluorine. So there is a formation of single bond between hydrogen and fluorine. So bond order is 1, which indicates the formation of this molecule, and between these two atoms there is a single covalent bond. So this is the one HF molecule and their molecular orbital configuration, and lastly we have seen the determination of molecular what is the bond order, and bond order is found to be 1. And one point is here is that in the hemodiagram it is observed that in the hemodiagram molecular orbital has energy which lies closer to the 2px orbital of fluorine than that of the 1s orbital of hydrogen. This is one important point. And molecular orbital formed in the case of HF molecule will not be symmetrical, and shape may be different when they get overlap. 1s and 2px overlap, then their symmetry is different. Okay, so orbital overlap, they are not symmetrical. So this is the hemodiagram for first molecule, HF molecule. And now second molecular energy level diagram we are going to see, that is the for carbon monoxide, CO. So this hemodiagram for CO molecule is given by Coulson. Coulson is the name of scientist. He has given the molecular orbital diagram for CO molecule, therefore it is known as Coulson hemodiagram for carbon monoxide molecule. So in case of this carbon monoxide, one is a carbon atom, second is oxygen atom, and as we know that, listen here carefully, that carbon have atom number 6 and valential configuration of carbon is 2s2 2p2. So we can write the configuration. All the 3 p orbitals are same, they have same energy. So all the 3 p orbitals are equal. We write the valential configuration for carbon. So 2s2 2px0 2py1 2pz1 we can write, because 3 p orbitals are equal. We can also take the px 1 2py1 2pz0 also. But now if we are writing in this way also, this is also correct. No, there is no any problem, that the configuration of carbon in the valential is 2s2 2px0 2py1 2pz1. And for the oxygen, valential configuration is 2s2 2px2 2py1 2pz1. It is okay. So this carbon and oxygen have valential configuration. Carbon have atom number 6 and oxygen have atom number 8. So 1s orbital in both the cases completely filled. So this is the valential configuration for carbon and oxygen. Now here 2s orbital of carbon and 2pz orbital of carbon undergo hybridization and forming new orbital which are represented by the symbol sp(c), C for carbon. Similarly, 2s orbital of oxygen and 2pz, only 2s and 2pz orbital of oxygen undergo hybridization and forming the new orbital which are represented by the symbol sp(o), O for oxygen, sp, because we are mixing s and p, therefore new orbital formed is known as sp and O, and sp(c) and sp(o). In case of this sp, I will repeat it, 2s orbital of carbon and 2pz orbital of carbon undergo hybridization forming a new orbital represented as sp(c). In case of oxygen, 2s and 2pz orbital undergo hybridization and forming new orbital represented as sp(o), O for oxygen. So after hybridization, the electronic configuration of carbon and oxygen are, now we can write in after the hybridization, now we write the configuration of carbon and oxygen again. Now write first the hybrid orbital, they have lower energy. So sp(c)2, because here 2s2 is there, after mixing they have hybrid orbital have same energy, and therefore 2 electrons are here, so write 2 electrons here, sp(c)2, and what is here, 1 electron, sp(c)1, and remaining 2 electron 2 orbitals are as it is, 2px0 2py1, right, the remaining 2 orbital in the same as it is. In case of oxygen, we can write, we have mixed 2s and 2pz, so what is new orbital is sp(o). So sp(o2), 2 electrons was there, sp(o1), 1 electron is here, therefore write first hybrid orbital new orbital like first. So sp2, spo2, spo1, and remaining two orbitals are as it is, 2px2, 2py1. So this is the new configuration for carbon and oxygen. Now what is the hemodiagram? So from this configuration it is known that there is a one, already this orbital have two electron, means this is the lone pair on the carbon. Again this, in this case of oxygen, there is a two electron in the orbital, therefore there is a one lone pair on the oxygen. So these are the two lone pairs, one is on oxygen, carbon, and the other is on oxygen. And now hybrid orbital of carbon, hybrid orbital of oxygen overlap and forming two orbital, sigma sp and sigma star sp, bonding and anti-bonding. spc1, spo1 overlap and forming two orbital, sigma sp and sigma star sp, bonding and anti-bonding molecular orbital. And this px and py, and this px and py overlap and forming pi to px and pi star to px, pi to py and pi star to py. So bonding and anti-bonding molecular orbitals are formed. All these formation of bonding is shown in the molecular orbital diagram of CO molecule given by Coulsons. So this is the hemodiagram for carbon monoxide, and this diagram is given suggested by Coulsons, the scientist. So as we have seen the configuration now, here oxygen have SPO, two electrons are there. This is the compartment for oxygen, this is for carbon. So see, this is the part of carbon and this part is for oxygen, and in the middle there is a carbon monoxide. Again AO are here, molecular orbital shown in the middle. So now the molecular orbital energy level, this in this case the lone pair of oxygen, that is SPO2, have lower energy and is here energy same lone pair. This is the SPO lone pair, the LP for lone pair. So one is complete. After that SPO1 and SPC1, the singly filled hybrid orbital of carbon and oxygen, SPC1 and SPO1 overlap and forming sigma sp and sigma star sp, bonding anti-bonding molecular orbital. Now second lone pair of carbon, SPC2, having the energy here and kept here, this is another lone pair which is on carbon, and three part is complete, one and the second and this third. Now x and y, 2px and y, 2px and y. In case of carbon only one electron is here, and in case of oxygen there are three electrons. So total 4 electrons are there. This x and y orbital of 2p orbital of oxygen and carbon overlap and forming pi x and pi y, bonding, and pi star x and pi star y anti-bonding molecular orbital. In this way, this is the hemodiagram suggested by Coulsons. And again I am repeating here that lone pair of oxygen having this low energy, and energy of carbon is having higher energy. And now in this case we have seen that how the molecular orbitals are formed. Now in case of SPC, it is the hybrid orbital having the lone pair, and has, in case of carbon, has higher energy as compared to that having a single electron. It means that it has a higher degree of p character and it is very reactive. Also SPC point away from the oxygen atom. And in case of oxygen, SPO2 hybrid orbital having lone pair has a lower energy than having a single electron. It has high degree of s orbital character and hence is very stable, that is unreactive hybrid orbital. So these are the reasons that SPO having lower energy, SPO is having lower energy than this one singly occupied, SPC having higher energy as compared to the singly occupied hybrid orbital of carbon. So, and this is the hemodiagram shown here for carbon monoxide, and on the basis of that we can write molecular orbital configuration and start from here, from lower to high. So SPO2 electron, this is lone pair, sigma sp b for bonding, sigma sp b 2, then pi x 2, pi y 2, then sp, this is another lone pair on carbon, then pi star x 0, pi star y 0, sigma sp star 0. And on the basis of that, now we, after writing the MO configuration, bond order of CO molecule is Nb minus Na upon 2. So Nb means number of electronic bonding. How many electrons are there? These are the 2 electrons and these are the 4 and 2, 6 electrons. Antibonding electrons, there is no any antibonding, star indicate antibonding molecular orbital. So star containing orbitals have no any electron and therefore the bond order is found to be 6 minus 0.3, so 6 by 2 is 3. So this shows that there is a triple bond between the carbon and oxygen atoms. So here bond order is 3, which indicate there is a triple bond. Their bond order is 3, triple bond present between the carbon and oxygen. So here this is the hemodiagram for CO and M molecular orbital configuration, and after that we can calculate the bond order for CO molecule, and the bond order is 3, indicate that carbon and oxygen in the CO molecule are linked together by the triple bond, 1 sigma and 2 pi bond. Okay, and similarly now we can see the hemodiagram for nitric oxide NO molecule. So next is similarly Coulsons treatment is there, only the in place of carbon. Now here is a nitrogen. So NO molecule contains 2 heteroatoms, one is nitrogen and second is oxygen. In place of carbon now here is a nitrogen, and the nitrogen have atomic number 7. So valence shell configuration is 2s2, 2px1, 2py1, 2pz1. Oxygen again same, 2s2, 2px2, 2py1, 2pz1. And again now here after this is the valence shell configuration, 2s and 2pz orbital undergo hybridization and forming the new orbital, which is represented by sp(n). And so here sp(n). In case of oxygen also 2s and 2pz orbital undergo hybridization and forming new orbital sp(o). Now this same configuration in after hybridization are shown here. Nitrogen sp, 2 electrons are there, therefore sp(n)2, sp(n)1 because of 1, and then remaining 2 are as it is, 2px1, 2py1. In case of oxygen, write first spo2 and 1 is here, spo1, and then remaining as it is, 2px2, 2py1. So this is the configuration. Again, as we know that this is the lone pair already paired, therefore this lone pair is present on nitrogen, this lone pair is present on oxygen. Singly occupied hybrid orbital of nitrogen and oxygen overlap and forming sigma sp bonding and sigma star sp antibonding molecular orbital, and these px and py overlap with the orbital of oxygen forming pi x, pi y and pi star x and pi star y bonding and antibonding molecular orbitals. Now this is the hemodiagram again suggested by Coulsons, and similar to that carbon monoxide. Now here this is the part for nitrogen and this is the part for oxygen, and in the middle there is a formation of molecular orbital of nitric oxide NO molecule. Again similarly here the sp hybrid orbital spo have 2 electrons, and this is the lone pair having the same energy, not taking part in the bond formation, and are shown here in the middle. After that singly occupied spo and sp(n) overlap and forming sigma sp bonding molecular orbital and antibonding sigma star sp antibonding molecular orbital. And now next one is the lone pair sp(n), having this is the lone pair which is present on the nitrogen, and now x and y, 2px and y, both the atoms of nitrogen and oxygen overlap. Total 3 electrons are here and 2 are here, 5 electrons. So here this orbital forming pi x and pi y and pi star x and pi star y bonding and antibonding molecular orbital, and distribution of electrons are total 5 are there, 4 are going in a lower energy orbital and the remaining 1 electron goes to the higher energy orbital, and presence of 1 electron in the unpaired electron in the pi star x orbital indicate that this molecule is a paramagnetic in nature. So this NO molecule is paramagnetic in nature because of the presence of 1 lone pair of electron on the one of the orbital pi star 2px, and on the basis of that also it is possible to write the MO configuration here. So NO molecule first, then column, then kk, then sigma 2s2, start from this here, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1 here, and on the basis of that bond order can be calculated. Formula is Nb minus Na upon 2. Number of bonding electrons are here, these are the 2, these are the 4. Number of bonding electrons in case of this, number of electrons are there shown here, 2 are here, and total 6 electrons are there, and anti-bonding electrons are there only one electron, and so 6 minus 1 5, 5 upon 2 2.5, this is not here correct. So number of bonding electrons are 2 are here and 4 are here, 6. So 6 minus only one antibonding electron, 6 minus 1, 5. 5 upon 2 means 2.5, 2.5. So 2.5 is the bond order. In case of nitric oxide, bond order is found to be 2.5, which represent 1 sigma, 2 pi bond and 1 unpaired electron in the antibonding molecular orbital. Due to the presence of 1 unpaired electron, NO molecule is a paramagnetic. So in case of nitric oxide molecule, bond order is found to be 2.5, which represent 1 sigma bond and 2 pi bond, and also there is a 1 unpaired electron in the antibonding pi star 2px molecular orbital. Due to the presence of 1 unpaired electron, NO molecule is paramagnetic. And in case of nitric oxide, 1 lone pair is of nitrogen, and on the oxygen also having 1 lone pair, and between two atoms there is a 2 bond of 2 electron and 1 bond is there of 3 electron, and therefore bond order is 2.5. So today we have discussed the molecular orbital diagrams for HF molecule, Coulsons M diagram for CO molecule, and Coulsons M diagram for nitric oxide NO molecule. So here we have completed the molecular orbital theory of the MO diagrams and their calculation bond order.